Pardon the link. Good afternoon, I'm Dale Carmen, and I'm here to present our research entitled Assessment of Vision-Based Vehicle Tracking for Traffic Monitoring Applications for the Edison Cossatin Professorial Chair in Electrical Engineering. So first, before I proceed with my presentation, here is a brief outline. First, I will provide the main motivation of our research, followed by an explanation of what vision-based traffic monitoring is, and then we'll identify the problem and objectives of the research, and then we'll propose, and I'll show you the proposed framework, and finally our experimental setup, the corresponding results and analysis, and the conclusion and recommendation based on those results. So first, the main motivation of our research is due to the need to identify, to improve the transportation infrastructure in our country. So the statistics shown is provided by a study done by the Japanese International Cooperation Agency back in 2014. And according to the study, one of the solutions to such traffic congestion is or the implementation of intelligent transport systems as defined in this slide. So we need to implement intelligent transport systems in real time to possibly extract traffic information from the road or from the road networks, and applications of this ITS include smart traffic light control up to incident detection. And in particular, we focus on what we call the vision-based traffic monitoring, which uses camera sensors, which as compared to other types of sensors, have a wider field of view, can record much more complex information, and are easier to install and maintain as compared to those loop sensors, which needs to be installed in road networks. So before we proceed with the problems encountered in this such field, we'll proceed with the basic or typical vision-based traffic monitoring framework. So typically we have a video feed or a camera feed, which can be a live feed or a recorded video. And then for each such feed, we extract or process the video frame by frame. So first, we extract the current frame, after which, to reduce the processing time of the system, we can extract a region of interest and possibly apply distortion correction if we need to. After applying the region of interest, our next step is to perform background subtraction by modeling the image frame. So background subtraction models the background by computing the pixel values from the previous frames. So in this study, we will use 100 frames. So after applying background subtraction, we will subtract the background from this current frame, and we will extract what we call the foreground, as shown here. So the foreground should contain the vehicular blobs for vision-based traffic monitoring. From these blobs, we can extract information from the road network, such as we can classify the vehicles in this road, for example, based on their size in the image frame. So we can classify large vehicles such as bus or trucks, for example, and differentiate them from motors or sedans and SUVs. After performing background subtraction, our next step is to track each vehicle frame by frame. So we proceed with what we call multiple object tracking. So for multiple object tracking, we create what we call a bounding box that encloses those vehicular blocks, and then track them frame by frame. So here is the bounding box for the two vehicles inside the region of interest for the first frame. The succeeding frame, still shown in green, while the bounding box in yellow is the previous frame, and then another one shown in green again. So in this case, you can see that we can track vehicles by connecting successive bounding boxes. So that's what we call multiple object tracking, and we can use different appearance models to associate vehicles from each frame. So we will introduce those later. And from here, we can create what we call vehicle tracks. So each vehicle tracks correspond to one vehicle. And from those vehicle tracks, we can extract vehicular information from the road network, such as vehicle count and vehicle speed. So vehicle count can be extracted by just counting the number of vehicle tracks that was processed. And then vehicle speed can be computed by subtracting the time difference or the frame difference from the first point of tracking of a vehicle to the last point, and then dividing it by the frame rate of the video feed. So this is our typical vision-based traffic monitoring systems. However, the issues with such systems are that they are usually evaluated using different metrics. So these metrics are usually often incomparable, and in the field there also is a lack of a standard data set used for evaluation. So it's hard to compare different systems in the literature. And additionally, most multiple object tracking benchmarks are usually pedestrian-oriented, which may have different assumptions when we are tracking vehicles. Additionally, offline tracking is usually the ones which are compared from each other, but those are not feasible for real-time implementations, which is usually required for implementation of intelligent transport systems. Thus, a standardized evaluation is needed to determine the most suitable vehicle tracking system for traffic monitoring. So the objective of this research is to first create a standardized test bed for evaluating the tracking systems. And second is to evaluate and analyze the performance of each tracking system for different traffic scenes. And finally, to determine if the tracking performance, which is usually reported for most systems, if it affects the traffic measurement accuracy, such as traffic count and traffic speed. So for our methodology or for our experimental setup, first we provide a standard data set, which is taken from the University of Albany detection and tracking data set. So the original data set contains 60 traffic sequences containing daytime and nighttime scenes. For the daytime, there are three types of weather conditions, sunny, cloudy, and rainy. However, for this research, we limit the study to stable daytime sequences. So we do not include sequences which have shaky cameras and sequences which have a nighttime feed. So after doing that, we extract 34 traffic sequences from the original data set. And for those traffic sequences, we have annotations which are available. And since we will limit the analysis to the region of interest, we apply masking of the annotations available in the dataset. And afterwards, for the 34 traffic sequences, we have a total of 40,241 frames with a resolution of 540 by 960 and a frame rate of 25 frames per second. Also, a total of 140,000 bounding boxes from 2,200 vehicles are in this dataset. And again, it includes 3 weather scenes, sunny, cloudy, and rainy. Here is an example of the dataset. So we can see that the dataset contains different traffic scenes of different viewpoints. It can be towards the camera or away from the camera or sideways. And shown here, if you can see, are the bounding boxes or the region of interest we manually extracted from each traffic scene. And from each traffic scene, for the first 2 seconds, or for the first 4 seconds, equivalent to 100 frames, we extract what we call a background model. So from this sequence, the corresponding background models are the following. So you can see that it's almost just the road, so we can simply subtract this to get the position of each vehicle. So for the comparative framework, we will proceed with this. So first, we have manually generated frames. So we will apply a region of interest mask to reduce the processing time. And we will extract an initial background work from 4 seconds of each sequences. After those, we proceed to process each sequence frame by frame, extracting the region of interest, applying background subtraction to detect the vehicles, and applying different tracking systems to track vehicles frame per frame to determine the number of vehicles in that sequence and the vehicle speed of each vehicle. The tracking systems evaluated here or in this research is the following. So we have 3 main systems: state-based, histogram-based, and feature-based, which are mainly different appearance models that can be associated with vehicles. For state-based, we simply compare the bounding box from one frame to another to match a certain vehicle. The advantage of this is that comparing the overlap of bounding boxes can be computed very fast. However, it may fail since closely spaced vehicles might exist during heavy traffic. The next type of system uses histograms to match one vehicle to another, specifically color and intensity histograms. And the advantage of this is that it uses usually multiple hypotheses to track the vehicles. So it will predict the location of the vehicle in the next frame, and then it will try to match the nearest histogram based on the previous frames. However, this needs reliable initialization of the histogram. Since we initialize a vehicle with the wrong histogram, then tracking will not proceed. The last type of system is what we call the feature-based system, in which we extract feature points from each vehicle, and then to match one vehicle from one frame to another, we just count the number of matching feature points for each vehicle. So the advantage of this is that it can handle partial occlusions, such as merge and split procedures. However, the number of feature points might increase the complexity of the system, making it not possible to be implemented in real time. For the evaluation metrics used for each system, we will use multiple object tracking performance such as MOTA and MOTP. So MOTA is the accuracy of matching the hypothesis tracks to the ground truth bounding boxes, while MOTP is the average overlap for a certain vehicle. So we illustrate those here. So in this illustration, the green bounding box or rectangles are the ground truth bounding box, meaning that there exists a vehicle there. Meanwhile, the red is the detected bounding box for each vehicle. So for t is equal to 1, we have a green bounding box or a ground truth bounding box, but we did not get a vehicle there. So that is what we call a miss. For t is equal to 2, 3, and 5, we have a green ground truth bounding box and a red detected vehicles. And since what we call the IOU or the intersection over union value is greater than 0.5, so the IOU means the area of the intersection of the green bounding box and the red bounding box over the union of their areas. So if it's greater than 0.5, then it is most likely that the vehicle is really is matched. So for frames 2, 3, and 5, we have a vehicle fit. And meanwhile, for time t is equal to 4, we have an IOU less than 0.5. So since the IOU is less than 0.5, we have a vehicle miss. So to compute the multiple object tracking accuracy here, we simply count the number of ground truth bounding boxes. So for example, 1, 2, 3, 4, 5 for the first 5 frames. And then subtract the number of misses or false positives. So here we have 2 misses and 1 false positive, and then divided by the total number of ground truth bounding box So for this illustration, we have 5 minus 2 minus 1. So that's 2 over 5. So we have an accuracy of 40%. Meanwhile, for the multiple object tracking precision, we just average IOU values of the hits. So we have a hit for frames 2, 3, and 5. So the IOU value is the average of 0.5, 0.7, and 0.9. So the MOTB value for this illustration is 70%. Aside from multiple object tracking performance, we also have what we call track quality, which usually dictates how much or how accurately we track each vehicle. So first two is the mostly tracked targets. So it determines how much, how accurately, or how many vehicles did you track with accuracy greater than 80%. The next is the mostly lost targets. So it determines the number of vehicles you track with an accuracy less than 20%. And finally, we have other track quality metrics such as identity switching and track fragmentation, which will be visualized in the next slide. So for track quality, so for the identity switching, it is shown on the left. So for the frames 1, 2, 3, and 4, we are tracking a vehicle and we labeled it as vehicle red. However, after frame 4, we labeled the vehicle as vehicle blue. So the identity of the vehicle switched, so it is considered an error for this illustration. Similarly, for fragmentation, it occurs when there is a point in time where no vehicles were detected, such as shown in the figure on the right at frames 3 and 4. And finally, for our traffic measurement accuracy, which is the goal of this research, we measure the count accuracy and speed accuracy by matching the vehicle tracks. And since the count accuracy might not exactly reflect the accuracy of counting, since misdetections and false detections might cancel each other, we also implement what we call the count precision and the count recall to make sure that the accuracy is indeed accurate. So for performance testing, we compare the relative performance of each blob-based system in terms of multiple object tracking, tracking accuracy, and track quality, and in terms of traffic monitoring. The 34 test sequences for the whole data set is processed for the 3 systems, and the results are cumulative. So here are our results. So it's slightly misformatted. So the results show that state-based tracking has the most accurate multiple object tracking performance, while the feature-based tracking system has the best traffic monitoring performance in terms of count accuracy and speed accuracy. And when we analyze the results one by one, so for example, the histogram-based system has an unusually large amount of false negatives. So we can attribute it to the following. So the vehicle is tracked correctly in this case. However, in this case, after the next frame, the red bounding box fails to follow the red vehicle, the reddish vehicle there. So we have an additional false negative. So this is one of the flaws in our histogram-based system that we have implemented. Next is the high amount of false negatives again. So yeah. So in this case, the vehicle is lost, and we have another additional false negative. Next is the high amount of identity switches for the state-based and the histogram-based systems. So the high amount of identity switching can be attributed to the following illustration. So in this illustration, we have a vehicle encircled by the yellow circle with ID 114. However, in the next frame, due to detection errors from the background subtraction, the vehicle will split into three identities, 114, 127, and 128. So this incurs identity switches based on the bounding box overlap of those three red detections with the green bounding box. So this increases the amount of identity switches for both state-based and histogram-based systems. Meanwhile, for the high amount of false positive for the feature-based systems, it is attributed to the fact that the feature-based system tracks non-vehicular blobs. So here, even though there are no vehicles present in the two illustrations in the left and in the right, corresponding to a shadow or a track lane marking and a tree reflection, they are counted by the system, thus the high amount of false positive for the feature-based systems. And finally, we see that the traffic measurement performance of both the state-based and histogram-based systems are unusually low, particularly in terms of count accuracy. So this can be attributed to the fact that, again, similar to the previous slides, that there is what we call a vehicle fragmentation. So when vehicle fragmentation occurs, instead of counting one vehicle, we count three vehicles, for example, in this illustration, thus resulting to a lower count accuracy. So the same thing happens for the histogram-based systems. So so further analyzing, we check if what variable affects the precision of the systems. So analyzing the number of identity switches and the count precision for the 34 sequences, for the three systems, we plot the number of identity switches per vehicle in the x-axis versus the count precision for each sequence. So this is a total of 102 results from 34 sequences times 3 systems. And analyzing this using correlation, we see that we extract an information that there is an around negative 0.7 correlation between those two measurements with a p-value less than 0.1%, which means that the correlation is significant. So that it means that the number of identity switches per vehicle, or the IDS value, affects the count precision of the traffic monitoring system. So that is our main conclusion for the research. And for the conclusion, the use of labeled bounding box annotations to determine the vehicle count through positive makes it easier to determine the reliability of the count measurement accuracy of such tracking systems. And the feature-based tracking system has been found to be the best tracker in terms of traffic monitoring performance. And finally, the track quality affects traffic monitoring applications more significantly than traffic tracking performance. So instead of measuring the tracking performance of a traffic monitoring system, it is better to check its track quality to implement a better traffic monitoring system. So for our future work, we need to implement the following design considerations. So merging of fragmented vehicular blocks, identification of non-vehicular blocks, and the minimization of identity switching to make our systems much more accurate. And finally, implementation learning frameworks along with multi-threaded and GPU computing can be explored to make them more viable for real-time applications. So that is all for our presentation. So I would like to acknowledge Edison Cosetting for the professoriate chair in electrical engineering. That is all. Thank you. Questions? Yes, the region of interest that we extracted is manually determined. However, it is possible to automatically determine that based on background subtraction for the consequence. But to simplify the limitations of the system, we just selected an ROI such that the vehicles detected will be large enough.
Kasi meron dun sa ibang images na yung green is yung wrong incident.
Yes.
So merong mga iba na yung green is actually going beyond yung yung sinabi ninyo na ROI. So will that count as a miss for your case?
Yes, that will count as a miss. So one of the problems here is that we only process the region of interest. And anything that has an intersection with that is counted as a ground truth. So not necessarily, it does not necessarily need to be inside the region of interest to be counted as a vehicle. Thank you.
Kaya po meron mga